CERN was founded in 1952 in order to establish a world-class fundamental physics research organization in Europe. In 1954, the new organization was retitled the European Organization for Nuclear Research. Later, the laboratory was commonly known as the European Laboratory for Particle Physics. The history of CERN goes back to the end of the Second World War. Progressive scientists envisioned creating a European atomic physics laboratory. Due to finances, the joint laboratory would allow European scientists to share the costs of such a state-of-the-art facility. The first proposal for the creation of the laboratory was presented at the European Cultural Conference in Lausanne in December 1949. After the Provisional Council was formed, agreements were made to establish a site in Geneva. In 1957, the first accelerator begins operation. The syncrocyclotron, SC, was CERN's first accelerator. This accelerator provided the first particle in nuclear physics experiments. However, in 1964, the SC was only used for nuclear physics, while the new proton-synchrotron, PS, was used for particle physics. On November 24, 1959, the PS accelerated protons for the first time, and for a brief time it was the world's highest energy particle accelerator. CERN built new accelerators in the 1970s, which altered the role of the PS. The PS' new role was to supply particles to the new machines. In 1968, George Sharpak revolutionized particle detection. Previously, particle physics involved examining millions of photographs from the bubble chambers or spark chambers. George Sharpak developed a multi-wire proportional chamber, and this led to the detection of particles through individual amplifiers and intercomputer. Sharpak was later awarded the Nobel Prize in 1992 for physics. The world's first proton-to-proton collider came into operation January 1971, when high-energy particles from an accelerator slam into a stationary target. Most of the valuable projectile energy is taken up to the target recoil, and only a small fraction actually feeds the collision. To ensure a more efficient use of energy, physicists realized two beams could be fired at each other. Therefore, the intersecting storage rings, ISR, was approved for construction in 1965. Many new technologies and techniques needed to be developed. The developments proved successful, providing CERN with valuable knowledge and expertise for its subsequent colliding beam projects. In 1976, the superproton synchrotron, SPS, was commissioned. This was the first of CERN's giant rings, measuring 7 kilometers in circumference. The SPS was the main component to the CERN's particle physics program. The SPS also contributed to the discovery of the W and Z particles in 1983. In 1986, CERN began to test heavy ion collisions to understand the theory behind the Big Bang and the universe just after. The universe was too hot and dense for the existence of familiar particles such as protons and neutrons. Instead, there were quarks and gluons. These collisions were designed to assess the theory. In 1989, the Large Electron Positron, LEP, was built. During 11 years of research, LEP and its experiments provided a detailed study of the electroweak interaction based on solid experimental foundations. Measurements performed at the LEP also proved that there are 3 and only 3 generations of particles of matter. In 1993, the NA31 experiment at CERN published the first precise results on what is known as a direct CP symmetry breaking, which indicates more clearly the physics underlying the phenomenon. The precise results of matter to antimatter asymmetry is an important question to physicists, since this can answer questions relating to the beginning of the universe. Overall, CERN has been the leader in particle physics, also a leader in the technological developments that support the research. Even in the present, CERN is conducting invaluable research in particle physics, which can explain the early origins of the universe.